His name is Pip. You named him Pip because you bought him at a pet store when you were 19, and you were holding him in a plastic cup on the drive home. And he made a small, high-pitched sound that your roommate said sounded like the word Pip. The name stuck. That was 3 years ago. Pip is a White's tree frog. He is 9 centimeters long. He weighs 50 grams. He lives in a glass terrarium on your desk with a heating pad under one corner, a water dish in the middle, a small plastic log he sometimes sits on, and a humidity monitor that you check every morning. Because White's tree frogs need their environment between 50 and 70% humidity or their skin starts to fail. Pip's skin is the entire reason this video exists because Pip's skin is not like your skin. Your skin is a barrier. It keeps water in and keeps everything else out. Pip's skin is a bidirectional membrane. Water moves through it in both directions depending on humidity, temperature, and the chemical balance of Pip's body. When Pip is in water, his skin absorbs it directly into his bloodstream. He does not drink through his mouth. He drinks through his stomach. No, he drinks through his skin. The entire concept of drinking as a separate activity does not apply to Pip. His skin is his mouth when it comes to water. This is also why Pip is trapped. He cannot leave the terrarium. Not because the walls are too high, although they are, because the air outside the terrarium is too dry. Your apartment runs at 30 to 40% humidity depending on the season. That would kill Pip within 4 to 8 hours depending on how warm the room was. He would dehydrate through his own skin faster than he could absorb moisture from anywhere else. His lungs would dry out. His mucous membranes would crack. His organs would fail. Pip is not a pet that wandered into captivity. Pip is a pet that is kept alive by a controlled environment that perfectly mimics the rainforest canopy of northeastern Australia, where his species evolved. Every frog on Earth has this problem, all 7,000 species. They are one of the oldest vertebrate lineages still in existence. They crawled out of the water 370 million years ago as lobe-finned fish, and they evolved into amphibians, and they became the first vertebrates to colonize land. But they never completed the transition. They stayed tethered to water. They breed in water. They lay eggs in water. Their larvae are aquatic. Their adult skin requires moisture. They can die of dehydration in conditions that would be called comfortable by mammals. Every frog is a compromise between land and water that has been holding for 370 million years without fully committing in either direction. Pip does not know any of this. Pip knows that the heating pad is warm, the water dish is wet, and the crickets you drop in every few days are food. Pip's understanding of the universe ends at the glass walls of his terrarium. He has never experienced rain. He has never experienced sun. He has never experienced air that was not climate controlled for his specific species requirements. He is a biological fossil living in a $40 glass box. Now let the simulation begin. Start the clock 10,000 years into the future. Frog populations globally have shifted because the climate has changed. Some regions have gotten wetter. Some have gotten drier. The drier regions are eliminating frog species at an accelerated rate. Because dryness is the enemy frogs have never solved. But within frog populations on the edges of dry regions, the individuals with slightly thicker skin, slightly more efficient kidney function, slightly better water retention at the cellular level, are surviving when the rest die. Selection pressure for dryness tolerance is increasing across every frog lineage that borders on arid zones. The White's tree frog specifically has a head start on this problem. The species in Pip's terrarium already produces a waxy lipid coating on its skin. It secretes this coating when ambient humidity drops too low. The coating reduces water loss by about 70% during dry conditions. It is one of the most dehydration-resistant frog species on Earth. Pip's descendants inherit this trait, and they inherit it in populations that are now experiencing regular dry periods they never experienced before. 100,000 years. The waxy skin coating has improved. It now reduces water loss by 95%. The frogs can survive low humidity conditions that would have killed their ancestors within hours. They are spending more time out of their historical wet refuges and exploring drier microhabitats. Their lungs have changed. Frog lungs are simple sacs with limited surface area because frogs supplement lung breathing with skin breathing. Skin breathing requires moisture. The descendants have lungs with more internal surface area because they are relying less on skin breathing and more on true pulmonary respiration. They are breathing more like reptiles and less like amphibians. 1 million years, the transition is visible. The descendants of Pip's lineage no longer secrete waxy coating only during dry periods. They secrete it constantly. Their skin has become permanently water-resistant rather than situationally protected. This is a fundamental shift because amphibian skin has been permeable for 370 million years. These descendants are the first true amphibians to evolve fully impermeable skin. The impermeability creates new problems that they have to solve. Impermeable skin cannot absorb water, so these frogs have to drink through their mouths like reptiles and mammals do. They have developed a reflexive drinking behavior that frogs in your time do not possess. When they encounter standing water, they lower their heads and swallow it, rather than sitting in it to absorb through the skin. This is the first time in frog evolutionary history that a frog drinks the way tetrapods have been drinking for hundreds of millions of years. The reproductive strategy is still tied to water. These descendants still lay eggs in ponds and streams, and their tadpoles are still aquatic, so they can leave water as adults, but they cannot abandon it completely. Water is still the nursery. 5 million years. The reproductive strategy breaks. Some populations have started producing eggs with protective shells, not hard shells like bird eggs. Leathery shells like reptile eggs. The shells prevent water loss from the developing embryo. This means the eggs no longer have to be laid in water. They can be laid in moist soil, under leaf litter, in tree hollows. The tadpole stage is compressed into the egg itself. The embryo develops through the tadpole phase before hatching, and the creature that emerges is a small version of the adult frog, not a swimming larva. This is the single most important evolutionary transition in the history of tetrapods. It is called the amniotic egg, and it is what allowed reptiles to become truly terrestrial 320 million years ago. Until that point, no vertebrate could reproduce without returning to water. The amniotic egg changed everything, and your pet frog Pip's descendants have just independently reinvented it. The descendants that have this new egg type are no longer bound to water at any stage of their life cycle. They do not need water to lay eggs. Their adults do not need water to hydrate. They are not technically amphibians anymore. By the functional definition, they are something new. A terrestrial tetrapod lineage that emerged from amphibian ancestors without going through reptiles first. 10 million years. The water-independent lineage has spread across continents. They are occupying ecological niches that were traditionally held by small lizards, large insects, and certain small mammals. They are competing with these groups directly and in many cases winning. Because frog morphology has advantages that lizards and mammals do not share. Frogs can jump. The descendants retain the powerful jumping legs of their amphibian ancestors. In open terrain, a jumping small predator is harder to catch than a running one. Because the trajectory is unpredictable, and the animal can cover complex terrain that a runner cannot navigate. The descendants are jumping 3 meters in a single leap at body sizes around 15 centimeters. This is comparable to the jumping ability of modern grasshoppers relative to body size, but in a vertebrate. They hunt insects primarily, but they have shifted towards smaller prey items and have developed the ability to catch flying insects mid-air with their tongue. Modern frogs already have sticky tongues that deploy rapidly, but the descendants have improved the accuracy and speed significantly. They are catching flies and mosquitoes and small butterflies out of the air, at distances up to 40 centimeters. Their skin has continued evolving. The waxy coating has been replaced by true keratinized scales on the dorsal surface. Their bellies are still smooth, but their backs are covered in overlapping scale-like structures that provide additional protection against dehydration and physical damage. They look like a cross between a frog and a small lizard. 50 million years. The descendants have diversified into over 200 species across every continent except Antarctica. They have colonized environments that modern frogs cannot tolerate. Desert species that burrow into sand during the day and emerge at dusk to hunt. Mountain species that live above the tree line at elevations where no modern frog could survive the dryness and cold. Arctic species that hibernate through winter months in frozen soil and emerge in summer to breed during the brief thaw. The desert species are the most extreme. They have lost all association with water. They obtain moisture entirely from the prey they eat. They can survive 6 months without drinking. They burrow into sand and enter a state called estivation, where their metabolism drops to almost zero. They emerge only during rare rain events or during the coolest parts of the night. They look less like frogs and more like small reptiles with folded legs and scaled skin. Some lineages have gotten larger. A 30-centimeter terrestrial predator has emerged in several regions. It hunts small mammals and large insects. It has retained the explosive jumping ability of its ancestors, but combined it with prolonged ambush behavior. It hides in vegetation for hours, waiting for prey to pass within range, and then launches itself up to 5 meters through the air to intercept. This is a predator that does not run or stalk. It waits and then strikes from distance using raw biomechanical force. 100 million years, the lineage has produced something that crosses a line that amphibians were never supposed to cross. A fully terrestrial predator, the size of a small dog that hunts in packs. It is 50 centimeters long. It weighs 4 kilograms. It has scales covering its entire body. Its jumping ability has been reduced in favor of sustained running on powerful hind legs. It walks bipedally for short distances and drops to all fours when running at speed. Its skin is completely waterproof. Its reproduction is entirely terrestrial, with amniotic eggs laid in protected burrows. Its diet is carnivorous. Its social structure involves coordinated hunting in groups of 3 to 8 individuals. This is not a frog. This is a frog's descendant that has converged on the same ecological role that small theropod dinosaurs occupied 100 million years before Pip was born. The body plan, the hunting strategy, the social structure, the dietary specialization, all of it has arrived at a similar solution to a similar problem. The frog lineage independently evolved toward a small dinosaur body plan because the ecological niche rewards it, and the starting material was adequate. The descendants communicate vocally. Frogs have always been vocal. Male frogs call to attract mates. These descendants have expanded that vocal capacity into complex communication, with over 30 distinct calls used in hunting coordination, territorial defense, and social bonding. The calls vary regionally, which means cultural transmission is happening. Different populations have different dialects. 200 million years. The frog lineage has occupied niches across the planet that no amphibian ever reached. There are flying descendants, true flying, not gliding like some modern tree frogs do in limited fashion. The flying descendants have developed wing structures from modified forelimbs and skin membranes that stretch between elongated finger bones. They are approximately the size of large bats, and they hunt flying insects at dusk, using echolocation that they have independently evolved. Flying frogs using echolocation. A sentence that would have sounded absurd to the person holding Pip in a plastic cup on a drive home from a pet store. But given enough time and enough selection pressure, the lineage has produced it. Because the starting material contained sufficient variation and the ecological opportunity was there. There are aquatic descendants too, but not in the way their ancestors were aquatic. These are fully marine frogs. They live in the ocean. They are salt tolerant. They dive to 50 meters. They hunt fish and cephalopods. They look like small cetaceans with the characteristic frog face and the powerful jumping legs reduced into flipper-like paddles. They are frogs that went all the way into the water that their ancestors had been tethered to for 370 million years. And they committed fully, rather than halfway. The terrestrial lineage that resembles small dinosaurs has produced something that could be called a civilization if the definition were generous. They build permanent structures. They dig networks of tunnels. They maintain defined territories with marker systems that include chemical signals and vocal announcements. They teach skills to their young. They coordinate hunting across territories with signal networks that span kilometers. They are not as intelligent as the raven lineage. They are not as socially complex as the gorilla lineage. They are not as technologically advanced as the hypothetical civilizations that might emerge from other species given comparable time. But they are more intelligent than any amphibian that has ever existed by several orders of magnitude. And they started from a frog in a terrarium on a desk. Pip does not know any of this. Pip is sitting on his plastic log right now, looking at nothing with the calm detachment of an animal that has no capacity for anticipation. His skin is glistening with moisture from the water dish. The humidity monitor reads 62%. The heating pad is warm. The crickets you added yesterday are slowly dying in the back corner. Everything is as it should be in Pip's universe. But somewhere in Pip's DNA is the genetic variation that his descendants will select for over 200 million years to produce everything from desert predators to flying echolocators to marine hunters to tunnel-dwelling civilization builders. The variation is already there. The mutations already exist in the population at low frequencies. Most of Pip's descendants will carry versions of genes that code for slightly more resistant skin, slightly more efficient lungs, slightly different egg structures. Selection will pick from this existing variation, generation by generation. The dramatic transformations happen through accumulated small changes that are already present as potential within the species right now. The frog on your desk is not finished. The frog on your desk is a checkpoint in a 370 million year evolutionary process that started when lobe-finned fish dragged themselves onto land and never quite finished the transition. Given another 200 million years, the transition completes. The descendants of Pip walk fully on land. They fly. They swim in salt water. They communicate in dialects. They hunt in coordinated groups. They stop being frogs, and the water dish in Pip's terrarium is just a reminder of where they came from before they figured out how to leave it behind.